So hello everyone. As we have discussed in our last class that we are going to do the video recording and then upload the session on the YouTube. So as per the plan, today we'll start this, and the reason being that there was bandwidth problem, bandwidth issues were there, and we were not able to uh, connect continuously. So you people were not able to hear me. So then we have thought about recording the session and then uploading it on the YouTube channel. So fine, uh, keeping this in mind, let's start the today's class. So today we are going to basically discuss about scaling. Okay, so scaling of the MOSFETs, and if time permits, then we will also discuss about the short channel effects. Okay, so as far as the MOSFET scaling is concerned, so you know about MOSFET, and we have in the last few classes we have discussed about the threshold voltage of the MOSFET and on what factors the threshold voltage depends upon, right? But you see, if we also discuss about the scaling, okay, if we try to discuss about scaling, then what do you mean by scaling basically? So scaling is whenever we talk about scaling, it is changing of the dimension. Okay, so the change related to the dimensions of the MOSFET. So basically, we want to reduce or increase the device dimensions. Whenever we reduce or increase the device dimension, we call it scaling of the MOSFET or scaling of the device, any device. Basically, as using MOSFET in various ICs nowadays, one of the biggest advantage is because this MOSFET is as a surface technology, and it provides like advantage of scaling. Okay, so scaling is can be easily done on surface devices, and basically as MOSFET is your surface device, so scaling is can be very easily done for MOSFETs rather than for the BJTs. Okay, so scaling means your changing of the dimensions. So basically, as I have told you, that it can be increase or decrease of the device dimension, but usually as we are advancing and the device dimensions are reducing, so our basic concern is to scale down the device. When I say scale down, it means to reduce the device dimensions. So as per the Moore's law, we know that the device dimensions the device area, whatever area the device occupies. So in approximately 2 years to 2.5 years, approximately 1.5 year to 2 years time, it becomes like half. Okay, so the area becomes half in every 1.5 year to 2 years. Okay, time. So keeping that in mind, if we see that if the area becomes half, then the device dimension, as we have already discussed in our big initial classes, first few classes, that the device dimensions also changes, and how it changes, that we will discuss today. And what are the if you change the device dimensions, then how your other parameters of the device gets affected. So the motto of the today's class will be sort of discussing the effect of scaling, and when we scale down the device, okay, so then what are the issues which comes up, and what is the how we can include that scaling into the device, scaling constant into the scaling in the various equations of the device, and then how these equations gets affected because of that scaling parameter. So that's what we are going to see today, and then later on we'll see that which particular type of scaling is better than, because if there are multiple types, if the scaling is of multiple types, then which one is better. So this is what our today's motto of the class is. So as you know that your MOSFET looks something like this, isn't it? In the figure, I have taken this figure from your reference book, which is Kang, which you are using presently. So in the Kang, if you'll see this figure number 3.24, so basically we see that the device dimension looks something like this, isn't it? So the device dimensions are your L, W, and this doping concentration of the source in the drain regions and the substrate region. So L is your device length, W is your device width, Tox is your thickness of the oxide. So this all parameters are without scaling. Okay. Then after scaling, let's say they will become something. So some constant will come. So where that constant should come, that is the biggest issue. So whether that constant will be multiplied or whether that constant will, that parameter will get divided by the constant. So how we can decide that? Okay, that is the most important thing when we do scaling. So you see, first of all, why we need scaling. So scaling is basically to satisfy the Moore's law, we have to scale down the device as well. So by scaling, what happens if initially we have X number of devices on the full substrate, on the whole substrate, then after scaling, the number of devices becomes twice, let's say. So the device dimension gets reduced and we are able to accommodate more number of transistors on the same area. So because of that, what happens? The device density increases. Okay. So as all of us know that nowadays we are using portable devices, and for the portable devices we want more functionality, and that functionality is provided usually by your processor. So to get more functionality and to include further features, what we want is complex processors, and like memories also we want higher space in the memory. So basically everything is provided by transistors. So we want more number of transistors on the particular area. So that's what the reasons are, right? So that's why we want to scale them down. Okay. So what happens because of this? Let's see. So we'll talk about some scaling constant in the scaling, but in VLSI, as you know very well, that the change is only the constant thing. Okay. So VLSI is particularly so dynamic that continuously there is change, and the change is very rapid. Okay, it is not like a slow technology. Continuously and very fast it is changing, that everybody is aware of. So you see what happens, as I have told you, that to satisfy the Moore's law, what we have to do is reduce the device area becomes half in like 1.5 year or approximately 2 years of times. So to reduce the device dimension, to reduce the device area to half, what happens? As we have already discussed, that the device dimension, device length and width will get shrinked by 30%, because you see, if the area should become like previously the area is A, and later on you want the area to be 0.5 A, 50% reduction. Okay, so then what will happen? To accommodate twice the number of devices, obviously you have to reduce the device area to half. So if you want to reduce the area to half, then each of the device dimension will get reduced by 30%, because you see, to get 0.5 A, you have to, if I assume that each of the device is a rectangle, so then the area of the rectangle is length into width, right? So length and width, the product of this should become 0.5. So if it should become 0.5, then the length and width should separately reduce by 30%. So it should become 0.7 L and 0.7 W. So when you will multiply them together now, so it will become 0.49 whatever the previous area was. So A dash will become, new area A dash will become 0.5 the previous area. So 0.5 the old area. So 0.5 A, let's say. So you see, your area is reduced to half. But to reduce that area to half, your device dimensions get reduced by 30%. Okay, so to satisfy the Moore's law, we have to reduce the device dimensions in every 1.5 year or 2 years or 2 years, approximately 3 years of time. The device dimensions get reduced by 30%. Okay, so by that what happens? So by doing this, the thing which happens is your device, more number of devices you can accommodate, and as the device dimensions reduces, the device also, If you'll see that previously you are able to buy a chip in, let's say, $1 or 100 rupees, let's say. So later on, the same chip, if you are able to buy at the same price, but the number of devices gets double, so obviously the cost per device, per transistor will be reduced or will be half. So you see, the transistor cost, per transistor cost will reduced, so the transistor becomes cheaper. Then also, as the device dimensions itself get reduced, so obviously the time the electrons will, the charge carriers will require to travel will also be small, so the device will be faster, right? But the other thing is like when we like improve the device and we scale down the device, usually we have to work on the wires, the connecting wires, the wires which are used to connect one transistor with the other. We have to work on them separately. If we leave them without like any without improvement, if we don't improve them, so then what happen? Whatever advantage we get because of device shrinking, we may lose it because we have not scaled the wires. Okay, so usually wires we don't improve, but it may affect our very much. It is going to very much affect our device performance. Okay, so that's what the thing is. Now you see, for discussing this scaling factor, so that 0.7 what I have told you is your scaling factor, okay, and the typical value of S is like 0.7, okay. So if we talk about 0.7, because you see how you got this 0.7, you know it now, that if suppose your length earlier is L and if you reduce it by 30%, so the new device length will be 0.7 L. So that 0.7 is this. So usually writing 0.7 all the times, you denote it by, let's say, S. Okay, so your S is nothing but 0.7, let's say. But rather than denoting it by, sometimes in some of the books you will find that rather than denoting it by 0.7, it is denoted by inverse of 0.7. So if you take 1 divided by 0.7, so it will become approximately 1.4. Okay, so the value of S is somewhere near to 1.4. Okay, so the typical range of S is 1.2 to 1.5. And why you get this 1.2 to 1.5? I have already told you that it depends upon your like 0.7. And why there is a range, why it is not a constant value? The reason being that whenever we scale down the device, it is not always like a dumb shrinking. When I say dumb shrinking, it means that it is not like theoretically you have calculated that to reduce the device area to half, you have to shrink the device dimensions by 0.7. The things are not like practically, it is not so. Whatever you have calculated theoretically, it roughly applies to the this practical thing, but the device dimensions may be somewhere near to that. Sometimes it becomes 0.6 and sometimes it may become 0.8 as well, okay, onto the next technology. So considering that there is always a range of S, that's what I have told you, it ranges from 1.4 to 1.8 rather than treating it as constant as at 1.4, okay. And it depends upon your technology nodes, as I have told you. Technology nodes means in the 90s, as I have told you, in the 90s, 2000, we used 0.5 micron technology, and nowadays we are using 11 nanometers, 7 nanometers, isn't it? Earlier, before that, before this 11 nanometer, we used 22 nanometers, okay, 45 nanometers. So this technology node is this, and this technology node is the minimum device length which you can use. So that whatever I have told you is the minimum device length. Okay, 45 nanometers is the minimum device length, let's say. Nowadays we can see it is 22 nanometers or 11 nanometers. The devices are manufactured at 11 nanometers. So 11 nanometer is the minimum device dimension which you can keep. You cannot reduce the device dimension for that particular technology node lesser than that. Okay, so that's what we have to keep into mind. Okay, so you see, so we understood that what is our scaling, and basically when we scale down the device, there are like scaling we can do by two methods. Okay, so one is called constant field scaling and the other one is called constant voltage scaling. Okay, so what is this constant field scaling and what is this constant voltage scaling that we are going to see now. Okay, and the remaining things I think we have already discussed. Small geometry effects probably we are going to discuss in today's class or in the next class, probably in the next class. But capacitance we have already discussed. Okay, so MOSFET scaling. So you see, reducing of the device dimensions itself, MOS, and also the interconnects, but we have to do that separately. Okay, if we just reduce the device itself, then it doesn't mean that we have reduced the interconnects itself, interconnects also. But for better performance, but for overall better performance from one technology to the another technology, we have to like resize the interconnects as well. Not only the device, scale down the device, but we have to scale the interconnects as well. Okay, so that's what we should keep into mind. We should keep that into mind, right? Okay, now you see this as I have told you that we use two type of scaling. So first one is called full scaling, okay, and that is constant field scaling, whereas the other one is called the constant voltage scaling. So what is the basic difference between two? So constant field scaling is when you keep your electric fields constant into the device, okay, and keeping that into mind that your electric field in the device should remain constant, and if you want to keep that electric field constant and you reduce all the device dimensions, keeping that particular thing constant, to keep that electric field constant, whatever you do, okay, reduce all the other dimensions, because you see if you talk about the electric field, then your electric field is basically E is equal to dV by dx, minus of dV by dx. So if you are talking about voltage and the device, this oxide thickness, so to keep the electric field constant, you have to reduce the voltage and the device, this oxide thickness, by the same factor, then only the electric field will remain constant. Okay, so when you do constant field scaling, so basically your purpose is to keep the electric field constant, and to keep that electric field constant, you reduce all the other dimensions like accordingly. Okay, but the other method of scaling is constant voltage scaling. So what is constant voltage scaling? So constant voltage scaling is you keep your all supply voltages constant without interfering with your supply voltages. You like change the other device dimensions. Okay, so if you follow one method, if you follow the first one, then it is called constant field scaling. You reduce the device dimensions keeping the electric field constant, then it is called constant field scaling. But if you reduce the device dimension, if you scale down the device keeping the supply voltages constant, then it is called constant voltage scaling. Okay, so that is what the difference between the two. Okay, so you see this is like this, and now if we just see this particular thing, so I have tried to include all the things what this particular things, constant field and constant voltage scaling, how these things are going to affect your various device parameters. Okay, so we'll see this in a short table. Okay, you can refer the things in detail from the book, but in short, and I'll try to explain them here from the single table, but writing everything in a single table gives you better visibility of the things, that how the things are changing. Okay, so we'll try to understand the things here, and some of these things which are not easy, some of the particular parameters which are difficult to understand, that how they are changing, that we will see later on, okay, in the next few slides. So you see L is very easy to understand, that when you have to do constant field scaling, so what you do, constant field, okay, so electric field is constant. So let's say I am talking about the electric field under the gate. Okay, so if I talk about the electric field under the gate, so it should be the supply voltage at the gate which we are using, and the oxide thickness. So both of the voltages should be reduced by the same factor. Okay, and if I talk about the electric field between the source and the drain, so then I have to divide VDD by your this okay, device thickness, not the device thickness, but the this whatever material is there, the substrate material. So in both of the cases, if you will see, your this this will become, the supply voltage will also get reduced by, will be multiplied by the factor 1 by s, and your this thickness or the device length will also get multiplied by the factor 1 by s. Okay, so that's what the thing is. So when you do constant field scaling, so length, width, oxide thickness, supply voltage and the threshold voltage, all of them get multiplied by the factor 1 by s. Okay, or you can say they are divided by s. Okay, but when you do constant voltage scaling, then you have to keep your supply voltage constant. So if your supply voltage is constant and you keep the threshold voltage constant, let's say, so then what happens? Your device dimensions, if you will see the formula for the this threshold voltage, so then we'll see that length, width and the gate oxide thickness we need to reduce by the scaling factor, right? Okay. Now from this doping density I have not discussed, but because that doping density is little difficult to understand, so that I will discuss in the next slide. Okay, but if we discuss about this area and the other parameters, so area, as you know, that if we have reduced width and length both by the factor of s, then your area will become what? Let's say W is reduced by W is, the new W becomes 1 by s, and the new length also becomes 1 by s of the previous length, then the total area will be reduced by s square. Okay, so that's what it is shown here. So if you do it by constant field scaling or by constant voltage scaling, and you take the parameters from the above this above cells, then you will see that the area area gets reduced by the factor of s square. Okay, then if you talk about the beta, okay, the beta is your transconductance parameter. Okay, so this parameter, process parameter, if you talk about, which is mu n Cox W by L. So if you talk about mu n Cox W by L, which is denoted by beta, so if you substitute everything from your previous table, so W and L like will get cancelled by each other, whereas Cox, if you see the Cox, then Cox is what? Epsilon ox by Tox, right? So epsilon ox is although constant, and Tox you have reduced by 1 by s. So your this new Cox dash will become what? S into Cox. Okay, rather Cox will change, whereas the other things mu n, W and L, mu n will be constant, W and L are changed by the same factor, then your beta, okay, this process parameter will become will get multiplied by s. So that s factor comes like this. Okay, then if you talk about the drain to source current, okay, so the drain to source current, the basic equation for your drain to source current IDS is something like k by means kn by 2 and twice of VGS minus VT, okay, into VDS minus VDS square by 2. Okay, so you see this equation, if you think about in the linear and the saturation region, the equations are different. So I have told you that it is in the linear region, half of mu n Cox W by L VGS minus VT into VDS minus VDS square by 2, right? So considering this equation, if you see, if you substitute everything in the equation, what we have derived earlier as well, so you will see that in the saturation, the drain to source current equation become this 1 by s if for constant field, whereas for constant voltage scaling, the factor this drain current will multiplied by s. So I mean, you see the parameters are automatically changing. If you move from one technology to the another technology, then the area is reducing, the drain current is increasing by the factor of, let's say, s in one technology by one method, and it is reducing by the factor of s with another method. Okay, so that's what the point is. Then if you talk about the gate capacitance, so gate capacitance is we have already discussed this in our last class, that it can be calculated by width into length divided by your oxide thickness. Okay, so that also get affected. Substitute everything from the whatever we have seen in our this upper cells, So from that, if we substitute the values, then we will find this. Okay. So similarly, if you find the resistance of the device, so resistance is of the device is nothing but it is voltage divided by current. Okay. And as voltage is also scaled by the factor of 1 by s, and the current also get affected by 1 by s. So the transistor on resistance will be unaffected by constant field scaling, whereas it will change by the factor of 1 by it will change by the factor of 1 by s for constant voltage scaling, right? Okay. Then gate delay. Okay, so delay, if we talk about, so it is intrinsic delay. It is like whatever delay we are the for the gate itself. Okay, it is without considering the your wires interconnects. So if you consider the delay of the gate itself, then this will become of the gate itself, then it will become something like this, affected by substituting the values from the upper cells. So that's what we have to do. Then frequency. Okay, frequency for constant field scaling, it becomes multiplied by the factor s. For constant voltage scaling, it becomes multiplied by s square. Power dissipation is nothing but multiplication of drain current and the supply voltage. So substituting the things from there, so power dissipation gets reduced by 1 by s, gets multiplied by s square for constant field, and for constant voltage scaling it is multiplied by s. Okay, and power dissipation density. So although this power dissipation we have not discussed yet, but it is easy to see. Okay, that it is nothing but the multiplication of voltage and current, right? And power dissipation density, if you talk about, because you see in VLSI, although we are concerned with power, but we have to more concerned for power density. Okay, so power density is power consumed per unit area. So that is also important factor, because it is responsible for the heating. Okay, so you see the power dissipation is remains it remains unchanged after scaling. Okay, and it becomes it is multiplied by s cube for constant voltage scaling. So for constant field scaling, the power density remains constant, whereas the power dissipation density is multiplied by the factor of s cube for constant voltage scaling. Okay, so from this table we see that how the various parameters get affected if we choose one of the method, okay, over the other. So you see each of the method have its own advantages and disadvantages, because the things this for one method the area is, for area, as we can see that it is equally affected by the two methods, but the power dissipation and the other things get differently affected by the two methods. Okay, so you see depending upon the application or what we want to achieve, we choose the method, right? So from the previous table, one thing, this doping density was remaining. So let's try to understand that how our doping density, why this s and s square is coming in the table for this, okay, particularly in this table for doping density. So we'll see this here because it is easy to understand it from the formula. So you see in the last class we have seen that our junction thickness or the junction depth is dependent upon this formula, right? It is under root of twice epsilon Si upon Q, Na plus Nd upon Na Nd, and modulus of the phi 0, the built-in potential minus the applied potential, right? So that's what the things on which your junction depth depends, right? So the junction depth, if you see that if you see, the some of the things are constant, like epsilon Si is constant, 2 is constant, Q is constant. So if you'll see, the formula gets reduced to that xd is proportional to some voltage divided by your doping density. Okay, now you see, if we see this particular thing and you see this particular equation, the lowermost equation equation which we have written in terms of proportionality becomes more important to explain the things. Okay, it will be helpful to explain the things. So you see, if your equation is this one, xd is equal to square root of 1 upon or mod of v upon na, then if you multiply in that particular equation on both the sides by 1 by s, then what happens? Your equation will become 1 by s into xd is proportional to 1 by x square root of this particular thing, mod of va upon na. Now if you take this s inside, then you can see that what happens. Okay, so you can write the equation for two different cases. So when you are talking about constant voltage scaling, so you see your voltage is not changing, voltage remains same. So if voltage remains same, then if you bring the this s inside, so it will become s square. So the thing which is changing is Na only. So for constant voltage scaling, the doping concentration will become s square. Okay, if you'll scale down the device keeping the constant voltage scaling, so you have to do the doping concentration for the new device. You have to do the doping concentration which is scaled by the factor of s square rather. Okay, and if you do it for full scaling or the constant field scaling, then for that case you can write it as you see again the same thing, but now you can write it as separately. So s, if you will write one s with na and the other way s with v, then the equation will become something like square root of 1 upon s na into v by s, mod of v by s. So you see your doping concentration gets multiplied, you have to multiply, I mean the new doping concentration will be s times na. If your earlier doping concentration was na, then the new doping concentration will be s times na. Okay, and your voltage will be divided by the factor of s. So that's what was written in your this table. So you see constant field scaling, for constant field scaling the doping density particularly gets reduced by gets multiplied by the factor s, whereas for constant voltage scaling it gets multiplied by the factor s square, right? So that's what the thing is. So I hope I have like completed all the parameters in this table and we have not forgot any. Okay, if I forgot to explain any of the parameter, you can tell me, you can comment, okay, in the like this, you can comment there, and then later on I can explain the things to you, okay, if it is required. Okay, so this was about this. Okay, so now let's see that we have discussed two types of scaling. One is constant voltage scaling and the other one is constant field scaling. So let's see out of this two which one is better and usually which one is followed. So obviously it depends upon the application, but usually we follow constant voltage scaling. The reason being why we follow this constant voltage scaling, because you see if you are like moving from one technology to the another technology, sometimes it becomes difficult to scale down the voltages. Okay, and you want the voltages to be same. If the voltages are same, then obviously that particular if suppose your IC is used in particular application, so the terminal voltages are some terminal voltages you are getting. Okay, so now if you want to replace the IC which is used there with a new IC, then obviously the supply voltage should be, I mean the supply voltage at which that new IC should work should remain same. If that IC is not capable to handle those voltages, and if like those voltages which are available at the terminals now are like insufficient or very the new IC is not capable to handle those voltages. Okay, it cannot tolerate those voltages. If you apply those voltages, then that device or that IC may burn out. Okay, so then you see you cannot use the new IC, you cannot replace the old IC with the new IC, with the new scaled IC. So for considering this particular thing, we go for constant voltage scaling rather. Okay, so if you do constant voltage scaling, you can use same supply voltage to run the new ICs. So that's what the thing is. Okay, but when you do this, so what happens? Because of this, if you do constant voltage scaling, the current density increases, okay, and because of which this electron migration takes place. Electron migration and the heating of the interconnects takes place. So what is electromigration and self heating of the interconnects, that we will discuss in next 1 or 2 slides. But this is what the problem which you face, because you see the current density will be, if you do constant scaling, as we have seen that this current density gets multiplied by s cube. Okay, so if your current density earlier is, let's say, JD, then for a scaled device it will become s cube JD. Okay, and we can see it from the this upper equations as well, because id is reduced, w is reduced, xj is also reduced, id is multiplied by sd, w becomes w by s. So you see, these are the things which happens. Now area is reduced. Okay, so you see, for every like method for constant voltage scaling, the biggest advantage we see that we can use the new IC, we can replace the old IC and we can use the new IC instead of that old IC. Okay, but with that we have certain problems like the this metal migration or electron migration which you say, and the heating of the interconnects. So you see, these are the problems. So what is your electron migration? So electron migration is basically, your see, when a very high amount of current passes through your this wires, so then what will happen? The regions at which there is like imperfect formation, okay, or improper formation of the metal, then from those places the electrons starts getting migrating. Okay, they starts leaving the this particular wire. So then if continuously that takes place, then you call it electromigration. Okay, so that's what the thing is. So because of this high current density, the electron migration takes place. Okay, so it's self-explanatory, it is not much thing to discuss in that. And when you see the electron migration, so because of electron migration, what happens? This diagram, in the diagram you can easily see that the wires get broken up. So this wire may get broken up because of other reasons as well. Okay, so the breaking of wire may be because of electromigration. One of the reason of this this breaking of wire or burning of wire is because of this electron migration, this open circuit. Okay, so open circuit may become because of the electron migration, whereas the other reason is heating. So if you continuously like a very high current passes, so then what happens? The current produces the heating effect. So this heating effect is also responsible for your open circuit. Sometimes if your IC is burned out, or if some wire is burned out on an IC, so the reasons may be the electron migration and sometimes the heating as well. Okay, and electron migration is depends upon your which direction the current is flowing, because you see, usually your devices, PN junction is basically your a directional device. Okay, the current is not equal in the two directions, so that's why the electromigration depends upon your this current direction, whereas the heating is like, obviously it is the total amount of the average current on which it depends, the DC, the equivalent DC current, right? So these are the various reasons. So basically I think we have completed this particular thing, scaling, today. And the short channel effects, so again this there are many short channel effects, so I think we will complete this various short channel effects in our next class. So today I think we can stop here. So from next class, in the next class we'll discuss this various type of short channel effects, because you see when we scale down the device, what happens? There are certain other phenomena which comes into play when we were talking about the long channel device. Okay, so some we can use the crude equations, but when you go to the smaller level, let's say at the 11 nanometer or 7 nanometer, So at that small level, there are various, because the drain and source region comes very close to each other, and the devices also are very near to each other, in like very near proximity. So then what happens? There are various other effects which comes into play, and because of this, which the device current you cannot calculate by the equations which you have used earlier. The device current equations gets affected by certain other factors. So that these are the various factors which affects the device current equation. So these factors we'll see in our next class. Okay. So these are called short channel effects, because these effects are coming as we are reducing the device, the channel length. Okay, fine. So thank you for attending today's class. Thank you.